Okay, I'll start us off today. Good afternoon, everyone. Thank you so much for joining us. My name is Alyssa Kelly, and I'm the Research and Challenge Manager with Foresight Canada. Foresight is Canada's clean tech ecosystem accelerator, and we are the program delivery partner in Project Greenlight. In just a moment, I'll hand it over to my colleague John to introduce Project Greenlight, and after that, we'll hear from Ashley and Derek at the City of Vancouver, and they'll speak to the Neighbourhood Energy Utility Challenge. A couple of notes for the webinar. There will be ample time for your questions at the end of the session, so please feel free to type your questions in the Q&A box at any time or raise your hand in person during the Q&A period. We'll do our best to get to all questions, but for if any reason we don't get to them, we will follow up with you after to provide an answer. This webinar will also be recorded and posted publicly for distribution after the session ends. And on that note, John, please go ahead.
Thank you very much, Alyssa. Thank you very much, everybody, for attending today's webinar. My name is John McPherson, Manager of Economic Transformation at the Vancouver Economic Commission. This initiative is the Project Greenlight initiative, is the initiative that and program and platform that the city is going to be using to onboard proposals to address the NEU challenge. I think it's first important to highlight some of the challenges that cities around the world face today, including the City of Vancouver. These include achieving net zero emissions, 100% new renewable energy targets, and building smarter and greener infrastructure, like permeable pavement, green roofs, enabling IoT devices to create smarter environments, accelerating digital transformation, creating flexible procurement policies. And this is something the city is working hard to achieve, as evident by the launch of our Project Greenlight initiative, and also bridging the aspirations resource gap. That means we have a number of ambitious targets and goals that the city has set, and now we just need to bring the resources to bear to achieve those goals and targets. So one of the things that we did at the Vancouver Economic Commission, we launched Project Greenlight, and we consider this as a platform for innovation. Underpinning innovation in any urban environment are major infrastructure and asset owners, which are really setting the pace at which we can transform our region to become smarter and greener, more digitally enabled. And so what Project Greenlight is essentially is a platform to connect innovators with major infrastructure and asset owners for accelerating the deployment of innovative projects across the region. Next slide. And so these are the organizations that are part of this demonstration network: the City of Vancouver, Fortis BC, Translink, New Westminster, and Quadro Properties. What we're talking about today is the City of Vancouver's targeted call, a challenge that they've launched to support their goal to achieve 100% renewable energy by 2030. Essentially how it works is as a proponent or innovator, if you're interested in participating in the challenge after the seminar and you're interested in learning more, please visit the website. And if you're interested in applying and you think you have the technology and what it takes, you would create an account, complete a profile, submit an online application, and then pitch your solution if you're shortlisted to the NEU team. And then following that, if the decision makers at the NEU are interested in proceeding with the next steps, you would have the opportunity to deploy your technology within the NEU system. So this is essentially what we're trying to create, is a streamlined process to onboard your project proposal. Next slide. So here's the website, projectgreenlight.io, where you can find more details about the challenge, and also happy to pass you on to Ashley and Derek to explain more about the NEU challenge. Ashley?
Great, thanks, John. Let me share my screen here. Make sure that we're all set up. You able to see my screen, John?
Yep.
Okay. Perfect. So yeah, thank you. And thanks to Vancouver Economic Commission and Project Greenlight and Foresight for facilitating this challenge and hosting the webinar. My name is Ashley St. Clair. I'm a senior planner with the City of Vancouver and Neighbourhood Energy Utility. So I'm just trying to deal with some technical issue right now. Let's give me 1 second. Should be able to do this. There we go. Okay, sorry about that. Yeah, so I'm here today. I'll take you through some materials with my colleague Derek Pope, who's a senior engineer with the NEU group. And we hope that the session is insightful and that we're able to answer any questions that you might have on the challenge that we're facing. So as John mentioned, and you know, the challenge is to transition the NEU to 100% renewable energy by 2030. Today, we want to give a bit of policy background with respect to what's driving us, give an overview of the NEU and our operations, and talk about potential solutions and resources with respect to the Project Greenlight challenge, and of course, take any questions. So I wasn't sure where folks were going to be coming from in this virtual setting, but of course we're in Vancouver on the west coast of British Columbia. And I would say as of late, residents have been increasingly feeling the impacts of climate change, particularly with events like the extended periods of smoke from forest fires that we've been facing, the recent heat dome, and of course, sea level rise and flooding is always front and center. Being a coastal city. So under the City of Vancouver's Greenest City Action Plan, we've been working towards GHG reductions for some time. You'll see back to 2007. And recently, City Council unanimously declared a climate emergency, acknowledging that there is a great deal more to do and urgently. And as a part of the Climate Emergency Action Plan, Council set a target to reduce greenhouse gas emissions citywide to 50% of 2007 levels by 2030. So this is a quick snapshot of where Vancouver's community emissions are coming from. You'll see a significant portion, 54%, they're coming from natural gas use in buildings for space heat and hot water. So under the Climate Emergency Action Plan, there are essentially 6 quote unquote big moves that will allow us to achieve our carbon reduction targets. And you'll see highlighted big move 4 is really the driver towards zero emission space heat and hot water in both new and existing buildings. So there's a lot going on under big move 4, including carbon pollution limits for existing buildings, for new buildings, as well as facilitating access to renewable energy. And this is kind of a fun little diagram that puts it all together, but really this is where the NEU is situated and where within Big Move 4, we've committed to developing this roadmap to 100% renewable energy by 2030. So jumping into the NEU and I guess a bit of the origin story. So we're in Southeast Falls Creek and expanded to the Falls Creek area generally. But the Southeast Falls Creek area was initially a brownfield site, 80 acres historically used for industrial purposes. And in 2006, council approved a development plan that saw 6 million square feet of new development built out in that area, and that build out is nearly complete today. At the time in 2006, the decision was made to put in a low carbon district energy system to supply space heat and hot water to the buildings, instead of each building having its own natural gas boiler, which was the common practice at the time. So the system was developed as the first large scale sewage heat recovery system in North America. So yeah, I included this. I think this is kind of a neat photo, just showing the boundaries of Southeast Falls Creek, and you can see the scale of construction that was happening at the time in advance of the Olympics. And that was sort of when we laid the original foundation and kind of the original like pipes throughout the Olympic Village. So the utility became operational in 2010, just in advance of the Olympics. And we are owned and operated by the city, but we are financially self-sustaining. So that means that all of the costs are recovered through our rates. And we have seen significant growth since 2010. And we've actually expanded our boundaries a handful of times. I mentioned to, expand along Great Northern Way out towards Emily Carr and also into Mount Pleasant and Northeast Falls Creek. We now have 43 buildings connected, and we deliver 70% renewable energy. That's primarily through a mix of waste heat recovery from sewage, as well as renewable natural gas. And as I mentioned, we have a commitment to develop a roadmap to 100% renewable energy by 2030. At this point, I will hand it off to Derek to get into more of our kind of the operational pieces. And Derek, I don't know if you want to take the screen there. You're on mute, Derek, if you're.
Yeah, sorry.
Okay.
Technical. 2 years into the pandemic and I'm still struggling here, but no, thanks Ashley for all that good background content. This map will hopefully help orient people. It's a map of the NEU service area. And so what's being shown here is the polygons in red. Those are buildings that are currently connected to the system and are being serviced by the system. So they'd be getting all of their energy for heat and hot water from the NEU. And then in blue there, those are buildings that we plan to service as they redevelop. And so as Ashley was mentioning, the goal of the NEU originally was mainly around the Olympic Village in Southeast Falls Creek here. We've since expanded out east. Out here is Emily Carr University that's connected, and we'll pick up all of the development along the way there. We started expanding into Mount Pleasant, where there's going to be lots of residential and commercial redevelopment. We've got the Science World connected here, and we're looking at an extension to Northeast Falls Creek in the north here. Currently, we've got a couple sources of energy. Definitely our main source is here, the Falls Creek Energy Center, where we have currently 3 megawatts of sewage heat recovery, and we're about to add an additional 6.7 megawatts of sewage heat recovery. And so that's our main source of low carbon energy currently to meet that 70% target. And then we also use gas boilers. So we have 20 megawatts of gas boilers. Those are for peaking during the coldest days of the year and also for backup. We've also recently just deployed our first satellite boiler plant to improve the resiliency of the system and make sure that we're keeping up with the peak demands of the system as we grow and to help balance the loads on the system. And so that will really help the extension into Mount Pleasant here. We've got one building, one recent building, the Mountain Equipment Co-op office building, where we've started taking waste heat from the building and then putting it into our thermal grid. So instead of the building having cooling towers on the roof like it normally would, they instead installed a heat recovery chiller. And they were able to take that waste heat out of the chilled water loop, scale it up to temperature 70 degrees Celsius that they could then inject that energy into our grid. So that was a really cool demonstration. And we're actually getting about 1% of our annual energy needs off of that building. And we've also got currently a procurement out in Northeast False Creek. It's a call for low carbon thermal energy. And so we intend to build a distribution grid, but we're seeking energy suppliers that could plug into that node up there, which will one day ultimately interconnect with the rest of the system. So that's kind of the lay of the land currently. It's we're up to 42 buildings connected, and lots of growth ahead of us as this map shows. Just to I guess reiterate what exactly district energy is. Here's a pretty simplistic diagram to drive that home. At the core of it, it's a hot water distribution system, and so what we're showing here, first of all, is a sewage pumping station. We made the strategic decision to build our first energy center on top of this sewage pumping station, and so buildings from the neighborhood, they put sewage into the sewer network. That sewage is warm because we all have hot showers and dishwashers and stuff like that. And so warm water collects at a sewage pumping station before it gets pumped off to a wastewater treatment plant. We take some of that sewage into our plant and we extract thermal energy out of it using a heat pump. And we take that thermal energy and put it into our hot water distribution network. On particularly cold days, we can also use our gas boilers. And so water leaving the False Creek Energy Center, it's supplied between 65 to 95 degrees Celsius, depending on how cold it is outside. And that hot water then travels through some buried distribution pipings to the buildings. And within each building, we have what's called an energy transfer station. That is the interface between our system and the building's heating and domestic hot water systems. And so it's at the transfer station, which is basically a couple of heat exchangers where the thermal energy gets transferred from our system to the building. Cool water is then pumped back to our plant, and the cycle starts all over again. It comes back to our plant around 50 degrees Celsius. Here's a picture of what our sewage heat recovery system looks like. So what you're looking at is a heat pump, and it's really two heat pumps that can be run in parallel or series. Green piping signifies a sewage traveling through it. So sewage is pumped to this vessel here, which is the evaporator. The warmth of the sewage evaporates refrigerant within this vessel. And then that refrigerant is compressed to bring it to very high temperatures. And in this vessel here, we have our system water that we can then dump that thermal energy into and heat up. Our heat pump can heat up water as high as 81 degrees Celsius. And then if I were to do a 180 on this picture, you'd see a big open space reserved in the plant for expansion of the sewage heat recovery system. And as I mentioned, we'll be more than doubling the capacity that we're installing on the next stage. And we're kind of at that stage in our build out where we really need some more good baseload renewable thermal energy. So we're proceeding ahead with that project. This is what the distribution network looks like. So it's a two-pipe system, a supply and a return, buried pipes made of steel, pre-insulated, and they run along the roadways and then branch off and would tie into each one of the buildings. And they're designed to operate at up to 95 degrees Celsius and 1,000 kilopascals of pressure. We've got about 4 kilometers of pipe installed to date and a couple of fairly significant expansions of the system on the horizon. This is what the energy transfer station looks like. And so basically a heat exchanger for the building's heating loop, a heat exchanger for the building's domestic hot water loop. And so our hot water goes in one side of the heat exchanger, the building's cool water goes inside the other side of the heat exchanger, and there's a transfer of thermal energy within those boxes. The building gets hot water, we get cool water back. And so we have one of these installed in each of the 42 buildings connected to our system. We can monitor them remotely and ensure that there's reliable service taking place. This graph here is meant to give you an idea of the system temperatures that we'd require from any sort of energy generation project. So I've kind of alluded to them already, but basically our philosophy is to try and operate at as low a temperature as we can. But as demand picks up on the system, you have two ways of meeting it. You can pump more water faster, or you can increase the temperature of your energy supply to move more energy that way. And so what this graph is showing here is the temperature of our system water and the outside air temperature. And so as it's warm out, we supply at 65 degrees Celsius, and this is for a good majority of the year. But as it starts getting below 10 degrees Celsius, then we fairly rapidly start increasing the supply temperature, because that's, of course, when we start seeing a big significant increase in the demand on the system as the heating demand goes up. And this allows us to deliver 50 degrees Celsius to the building's heating system and up to 70 degrees Celsius to the building's heating system on the coldest days of the year. For domestic hot water, we need to be delivering 60 degrees Celsius, which is why we can never supply less than 65 C. And then some of the challenges that we face, these graphs should help to illustrate it, but it really revolves around dealing with the peak demands of the system. So what this top graph here is showing is the forecasted demand on the system by year 2035. But what should stand out is and so this is showing in kilowatts, and this is the different years of months of the year. What should really stand out is there's much higher demand on the system in the winter months, and so compared to the summer months. So we need to have energy generation that we can deploy during those winter months. The other thing that should stand out is there's quite a big variation daily as well, and that's driven by domestic hot water peaks. First thing in the morning, everyone wakes up around the same time and starts having showers and things like that. So we see a pretty dramatic spike in the demand on the system first thing in the morning and just as everyone's arriving home for the day. So that will be a big challenge for us. This graph down here is a load duration curve. So it shows the number of hours that the system's at various capacities or various loads. And it should give you an illustration of this challenge as well. So right now, and this is real data from 2019. So we have 3 megawatts of sewer heat recovery. And so that can run pretty much flat out and occupy a pretty large piece of the annual energy demand. But what you find is for less than 1,000 hours of the year, our loads are pretty big. And so the challenge there is economically meeting those loads using renewable energy. Generally, we like to select renewable components that we can baseload, get really good utilization out of them, and run them fairly continuously. Where the economics become more challenging is deploying renewable energy sources that can be turned on and off just when they're needed during those peak periods, be it seasonal or daily peaks. So that's one thing that we'll be grappling with as we try and transition to 100% renewable energy. This graph shows our forecast energy demand over time and how we expect to meet that demand. And so this y-axis is in gigawatt hours. So in 2021, this year, we'll see about 60 gigawatt hours, 60,000 megawatt hours of energy demand on the system. We'll meet that using our existing sewage heat recovery system. We'll also use some renewable natural gas. That'll get us up to our 70% renewable energy target. And then the remainder will come from conventional natural gas. You see that we're going to be bringing on 6.6 megawatts of sewage heat recovery through the expansion. And so that will really give us some energy security over the near term. But as we continue growing the system, there's still a lot of energy here where we need to figure out what the source of that low carbon energy is going to be. You can see that by 2035, our energy demand is more than double what our renewable capacity can deliver. So that's part of the purpose of today's workshop is understanding where we can secure that energy from. The other big thing is that in year 2030, we want to completely remove ourselves from natural gas. And so what we had been previously using natural gas for peaking and backup, we want to transition to that component to something that's fully renewable. All right, I'm going to pass it back to Ashley for a couple more slides to take us home here, and then we'll open it up for questions.
Hey, thanks, Derek. Yeah, so we've been able to lay out what the NEU is, our operations, and some of our challenges, and just wanted to loop back to the core challenge that we have in Project Greenlight, helping us transition to 100% renewable energy by 2030, and maybe talk about what types of solutions we're looking for. So it is a very open question. We're open to a diverse array of solutions. Baseline, they should be compatible with our operating conditions, but the solution doesn't necessarily need to be holistic in that it doesn't need to solve the whole problem. There will very likely be more than one solution, more than one tool, or more than one phase of implementation, especially as you've seen our growth pattern over the coming decade plus. So we'll need a whole toolkit to get us to that 100% target. And with respect to technology, we see solutions manifesting in different ways. As Derek emphasized, we obviously need to bring on additional low carbon supply, but there are big gains to be had through operational efficiency measures. For example, it will be really important for us to manage or shave our peak demand, potentially through storage of some form. Derek, you can go to the next slide, thanks. And yeah, so really wanted to lay out what is important to us. First thing is the carbon emission reductions. So whether it's a solution that reduces our carbon emissions immediately or through efficiency or brings on new renewable energy supply, that those emissions reductions are ultimately the goal. Cost is a really important piece. So cost is important because we operate as a commercial utility. So the costs that we incur flow through to our rates and are fully recovered. So we do need to ensure that our low carbon energy, thermal energy is affordable for our customers. Space is a really unique constraint to our utility. We're in a dense urban environment and we don't have the luxury of space. Space in Vancouver is very expensive. So we don't have that ability to, for example, and go forward with a large scale, solar thermal field that could work in other areas. So I guess what I would say is space is a really important consideration. when thinking about the ability to implement the solution. So we certainly invite creativity, but it's also not something that has to be 100% resolved in order to submit a proposed solution. Environmental impact, yeah, this is important to us as well. We want to minimize any other impacts on the environment as much as possible. So that's to the natural environment, like potable water use, air quality, or impacts to the urban environment, like noise impacts to neighbors, impacts to traffic, and things like that. And of course, it's really important that the solution is reliable, and it really should enhance the resiliency of the system, or help build the resiliency of the system. And yeah, for potential solutions, we've thrown a whole host of them up on here. So thermal storage, heat recovery and heat pumps, AI and smart technology for controls, alternative fuels. The list isn't inclusive. And yeah, we're really looking forward to seeing what types of opportunities come out of this challenge. Great, and yeah, this is our final slide. I wanted to throw up some key resources that provide good context, kind of sidebar information if you're looking to support your application. And a lot of these are found, I think most of these are found on the Project Greenlight website. The one I did want to flag was the video tour of the NEU. So we haven't been giving in-person tours over the course of COVID, and we traditionally give quite a few of them to residents and visitors. But there is a video tour that has Derek walking you through the False Creek Energy Center, which could be interesting for some of you. And yeah, that's all we have prepared, but we're definitely open to taking any questions.
Great. Thank you so much, Ashley and Derek. That was great. Very interesting. A few questions have come up, so I will just start with the first one. Could you talk to the cost of energy you're providing to the 43 buildings versus the market rate for other consumers?
Yes, yeah, we can definitely speak to that. So one of our key performance metrics is we benchmark against BC Hydro, and our goal long term is to not be any greater than 10% more than BC Hydro. Our projections for 2022 rates is that we will actually be on par with Hydro, which is the other the primary low carbon source of energy in BC. Of course, we're more expensive than natural gas, but natural gas is not a low carbon source. Yeah, I think I don't know, Derek, do you have anything to add around rates?
No, that's good. Yeah.
All right, thank you. Next question, how is the temperature of the sewage heat increased to the 70 to 90 degrees Celsius that you mentioned?
Right. So yeah, sewage is sort of lukewarmish. It comes into the plant at about 20 degrees Celsius on average. But it's through the use of heat pumps and the refrigerant cycle within a heat pump that you're able to take a very low grade heat source and scale it into something that's useful. And so, like a real quick description of how that works is basically the warmth of sewage is enough to vaporize refrigerant within the heat pump, and then that refrigerant is compressed to increase its temperature to a very high temperature, and then we introduce that refrigerant next to our system water, and we're basically rejecting all of that heat into our system water. So that's sort of a simplistic explanation of how it works, but essentially it's through the refrigerant cycle of a heat pump. We're cooling sewage and rejecting that waste heat into our system water.
Great, thanks, Derek. A question whether ground source heat pumps could potentially be an option to help fill that renewable energy gap.
Yeah, we've seen a couple local examples of district energy systems that are using ground source heat pumps as part of their energy portfolio. I think the one sort of consideration with that is you can't just take energy out of the ground, because you will actually deplete the thermal energy within a geofield. So those systems generally work better with a system that's both heating and cooling, so that you're taking energy out in the winter and putting energy back in during the summer. But geo is definitely one of the approaches that we would commonly screen when looking at expanding low carbon energy for district energy. Maybe the other challenge in a Vancouver setting is just the spatial requirements of siting a geofield. It would maybe need to be partnered with a new development or something like that. But that's one of the constraints there too.
That's a good point. Thank you. A couple questions about the resources available at the end. There will be a post-event message sent around with the recording of this webinar, these slides, and any relevant links that were mentioned. So those will be sent around to all attendees. And one other question about heat pumps. So they do take power, and someone's wondering whether or not that energy comes from BC Hydro or from another source.
Yeah, so it does come from BC Hydro. We're fortunate in BC that we've got a clean electrical grid. The really exciting thing about heat pumps is the efficiency that they operate at. And so looking at our sewage heat recovery system, we get about 3.5 units of thermal energy out of it for every 1 unit of electrical energy we put in to operate it. So that's called a coefficient of performance. So it operates around 300% efficiency, which is where you see sort of the really big gains for environmental and also on the economical side of things as well.
Great. Thank you. We do have a hand raised. Armin, would you like to speak to your question?
Sure, can you hear me?
Yes, we can.
So thank you for the presentation. Just a quick question. So I have a company in Vancouver, and we have a technology for harnessing the electricity coming from renewables. And just wondering, because the presentation was mainly about heat energy, does the challenge also cover electricity that is being produced by renewable energy to, for example, address the peak load that is happening in those areas?
I mean, definitely the focus for us is delivering thermal energy. If there's a way that you can utilize your technology, did you say it was electrical storage, or can you just repeat what it was on the electrical side?
Yeah, I think I am on mute right now. So yeah, so we can like control the electricity output from solar PV or wind power plant, for example, and then we can store it in battery energy storage system and then discharge the battery to actually meet the load requirement. But it is not a heat load, it's the electricity load.
Right, I see. Yeah, so it's not a perfect match, but I guess if there was, like some way of deploying that to meet the electrical demands of the energy centers that we use, and it came at a cost benefit, that's a possibility. But again, I guess we're drawing from already a very low carbon electrical grid. Like one thing we see in other regions is a lot of combined heat and power with district energy, so that they're producing both electricity and harvesting the waste heat. But that's less prevalent here because there's just less necessity for the electrical generation. We've already got the clean grid that's relatively cost effective to draw from. You know, it doesn't seem like a perfect fit, but you're certainly welcome to, if you think there's a way of working it into a thermal network, then that's an opportunity. One thing that people view potentially marrying things like solar and wind is when there's surplus electricity, rather than storing it in a battery, you could reject that into the thermal grid and make use of that surplus energy by storing it in the grid, or just putting it into the grid that way. So there is some room for a thermal network and an electrical generation to work together, and yeah, something for you to think about, I think.
Thank you.
Great, thanks for your question, Armin, and thanks, Derek. Another question, is there an issue with the cost of the billing for individual consumers in the NEU system?
You know, consumers are always very cost conscious, so it is a huge consideration for us. Currently, our cost of energy is, I think we're at about 11 cents per kilowatt hour. So it's been less than if you were using BC Hydro to heat or heat up your home, and that seems to sit fairly well with our customer base. But as Ashley was mentioning, like cost of energy production, and which will flow through to our customers, is a huge consideration in this, because there is a point where people will not accept increases in cost of energies. So it's something we're very cautious of and mindful of. Ashley, anything you want to add to that?
Just focusing on kind of the framing of the question, where it was mentioned individual consumerism, and I'm just wondering if that's linked to the way that we bill our customers, and it's primarily because we have the one energy transfer station for the building that is where we meter the energy going to the building. So as opposed to electricity, where units tend to be hooked up to BC Hydro directly, so you're able to get the bill for your unit. It's fairly typical for thermal energy networks to operate at the building level, so the bill goes to the strata, and the thermal energy is often those costs are often taken care of through strata fees, similar to if a building with multiple units had a boiler.
Great. So this question, I guess, is a little off topic as per the attendee who asked it, but it's interesting. Do you consider putting EV charging stations in the neighborhood? And would there be a need for managing the charging demand with heat pump demand?
I suppose for the first part of that question, there's a whole other group at the city who are the specialists in EV and EV charging, and the City of Vancouver's plan. So unfortunately, I probably can't speak to what their plans are. But I mean, if there's a question, I'd be happy to pass it on if there's a specific question about a specific neighborhood. Yeah.
Great. Thanks, Ashley. Well, if there's a specific question about a specific neighborhood, as Ashley mentioned, feel free to type that in the questions and we can try and get back to you on that one. One more question. In terms of the application, I know that environmental impact is a big important criteria for you. Would you require a qualitative or a quantitative explanation to assess the environmental impact from an applicant?
I mean, quantitative is always nice. It's always probably the best option, as it allows us to compare it to other options that we might have. If that's not feasible, then of course a qualitative overview would suffice.
Great, thank you. So I will put a last call for any further questions. Looks like we have gone through all of the current ones. So if there's anything, please feel free to either raise your hand or type it in. And we'll give a couple minutes, and otherwise we will close out at this point. But thank you very much, Derek and Ashley, for your time. It was very interesting and very explanatory. It gave a good overview of the system. I really enjoyed looking at the maps and seeing, as a resident of Vancouver, what the plans are. It's really interesting. So thank you for joining us, everyone. As I said, the recording, the slides, and the relevant links will be sent around afterwards. And if you have any further questions about the challenge, please feel free to reach out to Project Greenlight, and you can find our contact information on the Project Greenlight website that was shared earlier. So thank you, everyone.